Welcome to our presentation on stateful vs stateless architectures. Today, we'll delve into the fundamental differences between these two architectural paradigms, exploring their characteristics, advantages, challenges, and the scenarios where each excels. By the end of this presentation, you'll have a clearer understanding of which approach best suits your project's needs and considerations. So, let's dive in and explore the world of stateful and stateless architectures. In this presentation, we'll cover various aspects of stateful and stateless architectures to provide you with a comprehensive understanding of their differences and applications. Here's what you can expect. We'll start by exploring what stateful architecture entails, its defining characteristics, and examples of where it's commonly used. Next, we'll delve into stateless architecture, discussing its key features and typical use cases. We'll then conduct a comparative analysis between stateful and stateless architectures, highlighting their respective advantages, challenges, and considerations. Following that, we'll present real-world use cases for both stateful and stateless architectures, demonstrating their practical applications in various domains. Finally, we'll discuss important factors to consider when deciding whether to adopt a stateful or stateless architecture for your project, helping you make informed decisions. By the end of our presentation, you'll have gained valuable insights into these architectural approaches, enabling you to make strategic choices for your software development endeavors. Let's proceed to explore each topic in detail. Stateful architecture refers to a system that maintains session state or data throughout interactions. This means that the server retains information about the client session or context across multiple requests. Now let's look at the characteristics of stateful architecture. Session data is stored on the server, typically in some form of persistent storage. The server actively keeps track of client state, enabling continuity and context preservation throughout the user's interactions. It is commonly employed in applications where maintaining user sessions is crucial, such as e-commerce platforms, gaming environments, and collaborative tools. This diagram illustrates the concept of a stateful architecture, which is commonly used in web applications and server-side systems. In a stateful architecture, the client, e.g., a web browser or a mobile app, sends a request to the server with limited information. The server then fetches additional data or context from a separate state storage system, such as a database or an in-memory cache. The state storage component holds the application state, which includes user data, session information, and other relevant data required to process the request fully. By leveraging this stored state, the server can enrich the limited information received from the client and provide a more comprehensive response. This approach allows the client to send minimal data with each request, reducing network overhead and improving performance. However, it also introduces complexity in managing the state storage and ensuring data consistency across multiple requests and users. Stateful architectures are often contrasted with stateless architectures, where the server treats each request as independent and does not rely on stored state, instead relying solely on the information provided in the request itself. Stateful architecture offers a robust framework for managing user sessions and preserving contextual information throughout interactions. Let's delve deeper into the advantages and challenges associated with stateful architecture. Now let's look at the advantages of stateful architecture. First is preservation of complex user sessions. Stateful architectures enable the retention of intricate user sessions, allowing for seamless continuation of user activities across multiple interactions. This capability is particularly beneficial in applications where maintaining session context is essential, such as e-commerce platforms and collaborative tools. Next is facilitates personalized experiences. By retaining user session data, stateful architectures empower developers to deliver personalized experiences tailored to individual user preferences and behaviors. This customization enhances user engagement and satisfaction, ultimately driving business success. Lastly, simplifies management of user state. With built-in mechanisms for session management, stateful architectures streamline the handling of user state. Developers can easily access and manipulate session data, ensuring consistency and coherence throughout the user journey. Now let's look at some challenges of stateful architecture. First is scalability concerns. Stateful architectures pose scalability challenges due to the need for storing and managing session data on the server. As the number of active sessions grows, the infrastructure must scale accordingly, potentially leading to increased costs and complexity. Next is increased server load and resource consumption. The storage and maintenance of session data on the server impose additional overhead, resulting in increased server load and resource consumption. This can impact performance and scalability, particularly in high-traffic environments. Lastly, synchronization complexities in distributed environments. In distributed environments, ensuring synchronization and consistency of session data across multiple servers can be challenging. Managing concurrent access to session data and resolving conflicts require sophisticated synchronization mechanisms, adding complexity to the architecture. Despite these challenges, stateful architectures remain indispensable in scenarios where preserving complex user sessions and delivering personalized experiences are paramount. By carefully weighing the advantages and challenges, developers can design stateful architectures that effectively meet the requirements of their applications while addressing scalability and performance considerations. Stateless architecture represents a paradigm where each request from the client to the server is independent and self-contained, with no reliance on previous interactions. Let's explore the key characteristics and implications of stateless architecture. Now let's look at some characteristics of stateless architecture. In stateless architectures, each request sent from the client to the server contains all the necessary information to fulfill that request. There is no need for the server to maintain any state or context between requests. Unlike stateful architectures, stateless architectures do not store session data on the server. Instead, session state, if required, is managed entirely on the client side or via external services. Stateless architectures are prevalent in modern web development, particularly in RESTful APIs and microservices architectures. These architectures prioritize simplicity, scalability, and flexibility, making them well-suited for distributed and cloud-native applications. This diagram illustrates the concept of a stateless architecture, which is a common approach used in web applications and server-side systems. In a stateless architecture, the client, e.g., a web browser or a mobile app, sends a request to the server that contains all the necessary information required to process the request. The request itself is self-contained and does not rely on any additional state or context stored on the server. The server receives the request, processes it based solely on the information provided in the request, and sends a response back to the client. The server does not maintain any long-term state or session information related to the client or the request. This approach simplifies the server's design and implementation, as it does not need to manage or persist any state across multiple requests. Each request is treated as an independent transaction, and the server can process it without relying on any stored data or context. Stateless architectures are often preferred for their simplicity, scalability, and fault tolerance. Since the server does not maintain state, it can easily handle requests from multiple clients without worrying about state management or data consistency issues. Additionally, if a server instance fails, other instances can seamlessly take over without any loss of state. However, stateless architectures may require more data to be transmitted with each request, potentially increasing network overhead and reducing performance in certain scenarios. Stateless architectures are often contrasted with stateful architectures, where the server relies on stored state and context to process requests fully. Stateless architecture offers a decentralized approach to handling client-server interactions, where each request is treated independently without the need for server-side session management. Let's delve into the advantages and challenges associated with stateless architecture. Now let's look at some advantages of stateless architecture. First, it enhances scalability and performance. Stateless architectures excel in scalability, allowing for effortless horizontal scaling by distributing statelessness across multiple servers. This distributed nature enables seamless handling of increased traffic and ensures optimal performance, even during peak loads. Next is simplified deployment and management. With no reliance on server-side session storage, deploying and managing stateless architectures is more straightforward and cost-effective. Developers can focus on building independent microservices or APIs, facilitating rapid development and deployment cycles. Lastly, it facilitates fault tolerance and load balancing. Stateless architectures inherently support fault tolerance and load balancing, as each request can be processed independently by any available server. This decentralized approach enhances resilience, ensuring high availability and reliability in distributed environments. Now let's look at some challenges of stateless architecture. First is limited support for complex session-based workflows. Stateless architectures may struggle to support complex session-based workflows that require maintaining state across multiple requests. Applications with intricate user sessions or transactional workflows may encounter challenges in achieving desired functionality. And next requires additional mechanisms for session management. Without server-side session storage, stateless architectures rely on alternative mechanisms for session management, such as tokens or cookies. Implementing and managing these mechanisms effectively require additional development effort and may introduce complexity. While stateless architectures offer significant advantages in scalability, performance, and resilience, they may not be suitable for all applications. Developers must carefully consider their project's requirements, particularly regarding session management and data consistency, to determine the most appropriate architectural approach. In the realm of software architecture, the choice between stateful and stateless architectures carries significant implications for the design, performance, and scalability of an application. When evaluating these architectural paradigms, it's crucial to consider various features that differentiate them and understand how they impact the overall functionality and efficiency of the system. Let's delve into each feature in detail. Stateful architectures inherently involve the storage and management of session data on the server. This means that information about client sessions, such as user preferences, authentication tokens, or shopping cart contents, is retained and accessible across multiple interactions. This capability enables the application to provide personalized experiences and maintain context for users throughout their sessions. However, the storage of session data introduces overhead and complexity, especially in scenarios with a large number of concurrent users or complex session requirements. In contrast, stateless architectures do not store session data on the server. Each request from the client contains all the necessary information to process that request without relying on previous interactions. While this simplifies server-side management and reduces the risk of data inconsistency, it may limit the ability to maintain stateful interactions and provide personalized experiences. Stateless architectures are often preferred for their simplicity and scalability, particularly in distributed environments where horizontal scaling is crucial. Scalability is a critical consideration in modern software architectures, especially in applications with varying levels of demand or user activity. Stateful architectures may face scalability challenges due to the need to store and manage session data centrally. As the number of active sessions increases, the infrastructure must scale accordingly to accommodate the growing storage and processing requirements. This centralized approach to session management can pose limitations in terms of horizontal scaling, potentially leading to performance bottlenecks and resource constraints. On the other hand, stateless architectures offer inherent scalability advantages by distributing statelessness across multiple servers. Each request can be processed independently by any available server, without the need for shared session state. This decentralized approach enables seamless horizontal scaling, allowing the system to handle increased traffic and user load efficiently. Stateless architectures are well suited for applications requiring rapid scalability and elasticity, such as cloud-native or microservices-based environments. Performance considerations are paramount in determining the efficiency and responsiveness of an application. Stateful architectures may experience performance issues due to the overhead associated with session management. The storage and retrieval of session data on the server can introduce latency and processing overhead, particularly in scenarios with high concurrency or frequent session updates. As a result, stateful architectures may struggle to maintain optimal performance under heavy loads or during peak usage periods. In contrast, stateless architectures generally offer better performance characteristics. By eliminating the need for server-side session storage and reducing dependencies between requests, stateless architectures minimize latency and processing overhead. Each request is self-contained and independent, allowing for faster response times and improved throughput. This performance advantage makes stateless architectures well-suited for high-volume, real-time applications where responsiveness is critical, such as streaming platforms or real-time analytics systems. The complexity of managing stateful and stateless architectures differs significantly, impacting deployment, maintenance, and operational overhead. Stateful architectures require sophisticated session management mechanisms to ensure data consistency and reliability. Developers must implement mechanisms for session storage, retrieval, and synchronization, as well as handle issues such as session expiration, data persistence, and failover strategies. Managing stateful architectures often involves greater operational complexity and resource allocation, especially in distributed or clustered environments. In contrast, stateless architectures offer simplified deployment and management. With no reliance on server-side session storage, stateless architectures reduce the operational overhead associated with session management. Each server can operate independently, processing requests without maintaining session state. This decentralized approach streamlines deployment, scaling, and maintenance efforts, making it easier to manage and operate stateless architectures at scale. Additionally, stateless architectures are well-suited for containerized or serverless environments, where agility and automation are essential. Ensuring data consistency is crucial in applications where multiple users interact with shared resources or data sets. Stateful architectures inherently provide consistent session data across requests, as session state is centrally managed and synchronized. This ensures that all clients accessing the same session see consistent data and avoid conflicts or inconsistencies. Stateful architectures are commonly used in applications requiring strong data consistency guarantees, such as financial systems or collaborative editing tools. In contrast, stateless architectures may lack strong guarantees of data consistency, especially in distributed or asynchronous environments. Each request is processed independently, without shared session state, making it challenging to maintain consistency across interactions. While techniques such as idempotent operations or optimistic concurrency control can mitigate consistency issues to some extent, stateless architectures may be better suited for applications with looser consistency requirements or eventual consistency models. Fault tolerance is critical in ensuring the resilience and availability of an application, especially in distributed or cloud-based environments. Stateful architectures may face challenges in fault tolerance due to centralized session storage. A single point of failure in the session management layer can lead to service disruptions or data loss, affecting the overall availability and reliability of the application. Ensuring fault tolerance in stateful architectures requires implementing redundant storage, replication, and failover mechanisms to minimize the impact of failures. In contrast, stateless architectures inherently support fault tolerance through their decentralized nature. Each server can operate independently, processing requests without reliance on shared session state. This distributed approach enhances resilience and fault tolerance, as failures in one server or component do not impact the availability of others. Additionally, stateless architectures can leverage load balancing and auto-scaling techniques to dynamically adjust resources and maintain service availability during failures or spikes in demand. In conclusion, the choice between stateful and stateless architectures depends on various factors, including session data requirements, scalability needs, performance considerations, management complexity, data consistency requirements, and fault tolerance objectives. By carefully evaluating these factors and understanding the implications of each architecture, developers can design systems that effectively meet the needs of their applications while maximizing performance, scalability, and reliability. Stateful and stateless architectures cater to different use cases, each offering unique benefits depending on the requirements of the application. Let's explore examples of scenarios where each architecture excels. Let's look at the use cases for stateful first. Stateful architectures are well suited for e-commerce platforms, where preserving the contents of a user's shopping cart across multiple interactions is crucial for providing a seamless shopping experience. Applications like document editing platforms or collaborative whiteboards rely on stateful architectures to maintain real-time synchronization among multiple users. Preserving session state ensures that all participants see the latest changes and updates in real time. In online gaming environments, stateful architectures track player progress, inventory, and game state to provide a consistent and immersive gaming experience. This includes maintaining information about player achievements, levels, and in-game assets. Let's now look at the use cases for stateless. Stateless architectures are commonly used in RESTful APIs for mobile applications, where each API request contains all the necessary information to process the request independently. This approach simplifies development and ensures compatibility with various client devices. Stateless architectures are fundamental to microservices architectures, where each microservice operates independently and communicates with other services via stateless protocols like HTTP. This decentralization enhances scalability and flexibility in large-scale distributed systems. Serverless architectures, such as function as a service, leverage stateless functions that execute in response to events or triggers. Stateless functions are well suited for ephemeral compute tasks, offering cost efficiency and scalability without the need for server management. By understanding the specific requirements and constraints of your application, you can choose the appropriate architecture, whether stateful or stateless, to effectively address your project's needs and deliver optimal performance and user experience. Each use case presents unique challenges and opportunities, requiring careful consideration during the architectural design phase. When deciding between stateful and stateless architectures for your project, several factors come into play. Consider the following aspects to make an informed decision. First is scalability requirements. Evaluate the scalability needs of your application. Stateful architectures may encounter limitations due to data storage requirements, while stateless architectures offer better scalability by distributing statelessness. Next is session complexity. Assess the complexity of your session management requirements. Stateful architectures excel in managing complex session-based workflows, whereas stateless architectures may struggle with such intricacies. Next is performance considerations. Examine the performance implications of each architecture. Stateful architectures may experience performance issues due to session management overhead, while stateless architectures generally offer better performance by design. Next is resource utilization. Analyze the resource utilization patterns of your application. Stateful architectures typically consume more server resources due to session data storage, whereas stateless architectures are more resource efficient. Next is fault tolerance and resilience. Consider the fault tolerance and resilience of your architecture. Stateless architectures, with their distributed nature, often provide better fault tolerance and resilience compared to centralized stateful architectures. Next is development and maintenance complexity. Factor in the development and maintenance complexity associated with each architecture. Stateless architectures typically offer simplified deployment and management, while stateful architectures may require more complex session management mechanisms. Next is integration with existing systems. Evaluate how well each architecture integrates with your existing systems and infrastructure. Consider compatibility, ease of integration, and potential migration challenges. Next is regulatory compliance. Ensure compliance with regulatory requirements, such as data privacy laws and industry standards. Certain regulations may impact your choice of architecture, especially regarding data storage and management practices. And lastly, future flexibility. Anticipate future growth and evolution of your application. Choose an architecture that allows for flexibility and scalability as your requirements change over time. By carefully considering these factors in the context of your specific project goals and constraints, you can make an informed decision that aligns with your long-term objectives and ensures the success of your software development endeavors. And with that, we've reached the end of our presentation. We hope you've gained some valuable insights. If you have any further questions or would like to explore more, please don't hesitate to leave a comment. Thank you for your time and attention. Please consider subscribing. Your support means the world to us at Consultant Bot. Every like, subscribe, and share helps this channel thrive, and it truly means a lot.